Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous few lectures we have been discussing cluster analysis. So, this is going to be the last lecture of this particular technique, cluster analysis. So, in previous lecture we talked about k-means clustering. We understood the algorithm of this particular technique. We also did an exercise in R to understand the steps. So, what we discussed about k-means, these let us go through these steps quickly once again. So, we typically start with user specified number of desired clusters, that is k, then initial assignment of observations into these k clusters is done. Then after that clusters and centroids are computed, and once this is done, then in the next step for each observation is reassigned to the cluster with nearest centroid, and as a result of this recomputation of cluster centroids to adjust for the loss or gain of observation, that is done, and we keep on repeating these step 2 and then followed by and then step 3 till there is a decrease in cluster dispersion. So, this is these are the main steps of k-means clustering which we discussed in the previous lecture as well. Then in R also we talked about we did a small exercise and discussed how k-means clustering can be implemented. So, we took first 5 serials and then we assumed two cluster, first cluster with just first 2 serials and the second cluster with the remaining 3 serials, and we saw that when we compute the centroids and then when we start reassigning the observation into the closest centroid, then what happened, one of the cluster was actually got reassigned, and then when we repeated the exercise we saw that that was the final configuration, that all the observations, they were into their closest they were into the cluster with closest centroids. So, we in that exercise we have gone through the steps of k-means clustering. Now, let us discuss few more important points about k-means clustering. So, from the steps of k-means clustering, as we can see, selecting a suitable k for our clustering task is an important exercise which is part of this method. So, let us discuss a few points. How do we decide which is going to be the best k for our cluster analysis. So, selecting k, few important points, for example domain knowledge. So, sometimes domain knowledge will guide you in terms of the number of expected clusters. So, as you know that in k-means clustering we need to pre-specify the number of clusters that we want, and domain knowledge about the particular data set, about the problem at hand, can actually help us in terms of the clusters that we are looking for. For example, if we talk about the customer segmentation, so we can always understand that kind of income groupings that we expect from a target population, because we will have some pre-existing knowledge about the target population, like there is going to be a segment which is earning less than rupees 5,000 per month, then there is going to be a segment which is earning between 5,000 and about 12,000, then 12,000 to 25,000, and in that fashion we can have our own expectation from the target population. So, that kind of domain knowledge can always be used when we apply k-means clustering. Similarly, the practical constraint can also sometimes guide or in a way restrict us in terms of selecting the number of clusters. In many business applications, sometimes it might be difficult for us to plan our if it is about the customer segmentation, and that is to be used later on for the marketing and promotional schemes, then sometimes it might be difficult or costly for us to administratively or economically implement those schemes for a large number of clusters. So therefore, we might like to have fewer number of clusters and then come up with the promotional and marketing schemes for them and implement them. So therefore, the practical constraint, they could be administrative in nature or financial in nature. They can also put a limit on the number of clusters that we can select for our cluster analysis, specifically k-means clustering. So beside these two points, the remaining approaches, which could be the default approach more often than not, that we can try different values of k and compare the results and finalize. So we can go about doing our clustering. So we might have still we have to start with a given number of clusters that are more likely to be there, and then we can start with those number of clusters and experiment. So we can try different values of k and then compare the results, and based on that the best possible number of will be able to pick the best possible value for k. So start with expected number of clusters and analyze how sum of distances changes with increase or decrease in k. So as we talked about in the previous lecture also, so let us have a look at it again. So as we talked about that in non-hierarchical methods, we try to minimize this within cluster dispersion, and this sum of distances, sum of square distances of observation from their centroid. This is the measure that is typically used. So keeping this particular measure in mind, if we are trying out different values of k, then we can analyze for different values of k how this sum of distances is changing, because that is the measure, that is the metric that we use in k-means clustering, where we look to minimize the dispersion. So depending on the results, depending on this comparison, the number of the particular k value for which this sum of distances is probably lower, probably we can go with that value of k. So these are different ways in which we can select an appropriate value for k. So few other important points about k-means clustering. So let us go back to the algorithm. So there in the first point itself, we get that we need to decide a suitable value for k, and then you will also see that something that is mentioned in the slide also, that initial assignment of observation into clusters, how that should be done. So that can also play an important role in deciding your clustering results. So how initial partitioning of observations into a given number of clusters is to be done, that also we need to take care of. So few points which could be helpful in this decision that we have mentioned here in this slide. So let us discuss them. So first one is external information suggesting for a particular partitioning can be used. So if we have certain information that is not part of the data set itself, and it is suggesting that a particular kind of particular observations group of observation should be in certain clusters, should be in one group. So that kind of information can always be used. For example, if we are doing customer segmentation and we know that a group of customers, they are coming from a certain locality, they are coming from a metro city, or they might be coming from a tier 2 or tier 3 cities. So that kind of geographical clustering, that information can also be used for to implement this kind of partitioning. So because this step where we are doing initial partitioning of observation to k clusters can actually reduce our computation time. So if we are thinking about hundreds and thousands of records and applying clustering analysis, because as we know that we are into unsupervised learning method into that domain, and there typically we deal with a large number of observations. So therefore, anything that can reduce the computation time for us, that is always recommended and preferred. So as I suggested, for example, customer segmentation, if we can incorporate the geographical clustering, if we feel that that information is going to be important in our clustering process, in our clustering result, then certainly that can be incorporated in the partitioning, initial partitioning itself, and later on the algorithm will take care as the new centroids are computed and the distances of each observation from these new centroids are are computed. We can that reassignment and all those things are going to take care of the a good enough solution for us. Now let us move to the next point, that is external information about potential cluster centroids can also be used to allocate the observations. So if we happen to know the data set that we have, the observations that we have, and the problem domain that is there, the context of the problem that is there, we have some idea about where these centroids, the clusters and number of clusters and their possible centroids are going to be, then we can use that details about those centroids at their potential coordinates. If we have some idea about that, then that information can also be plugged into initial partitioning scheme of k-means clustering, and which could be a very good starting point to reduce in terms of reducing the computation time of this particular technique. So external information about particular partitioning or centroids itself can always be used in the initial partitioning. If we do not have these kind of information to help us in initial partitioning, then of course we can that is the default approach, where we can try different randomly generated starting positions and then select which one is more suitable, because there could be various candidate models even based on same technique, because different configurations could be there, especially in the context of cluster analysis. So therefore it makes sense to try different randomly generated starting positions and then use the best one that is there for later analysis. So let us move forward. So before we discuss further, let us go back to RStudio and do an exercise. So in previous lecture we did an exercise using just the first 5 serials, and then we understood how the k-means clustering can be applied and how what kind of results we got. Now what we are going to do is we will apply the k-means clustering on full data set and we will analyze the results later on. So let us go through few of the code. Let us run through few lines of code that we have to do for importing data set and other things. So let us load this library. Let us import the data set. Let us take a new copy of this data set like we have been doing in previous lectures as well. So some of the transformation steps are going to be common for k-means clustering also. So we will go through these transformations and then use it for applying k-means clustering. So we need to find that part of code where we had done the scaling of full data set, because now we are going to use the full data set. You can see here normalization of all variables. So let us go ahead with this. So we will normalize. So we can see here the variables that are part of this and first 6 observations. So, this full data set, these observations and variables are going to be part of our next k-means clustering. So, let us move ahead. So, now we will go back to the full data set part of code where we apply k-means clustering. So, this part we had discussed before, k-means clustering on first 5 serials. This part we have gone through in previous lecture. Now here, so we are now going to use full data set for k-means clustering. So here we are again using the value of k as 6. So let's have a look at the first 6 observations. So these are the first 6 observations. You can see the variables that are part of this. Now as you can see, a few of these variables they have NA values. So we'll get rid of these variables. So let's identify them. So you can see here in the code I have written 9, 10 and 12, 13. So you can see 1, 2, 3, 4, 5 and then 6, 7, 8, 9. You can see some NA values even in the first 6 observation, and 10 also. Then 11 seems to be fine. Then in 12 and 13 also, in the first 6 observation itself we are able to see some NA values. So that in the code itself also the same is reflected. Column numbers 9, 10, 12, 13 have been left out, and k-means is applied. So k-means is the function that we have used here. So and the second argument is where we specify the number of clusters that we want out of this clustering process. So let us go through this code. Now the model has been, k-means clustering model has been built. Now let us look at the cluster centroids. So there are many attributes which are returned from this k-means function. So we will access the important ones. So first one is where we get the cluster centroids. So this is the code, and then what we are doing here in the next line, row names, we are changing the names of row names to reflect the centroids. This is done. Now next thing that we are going to do is the distance of observations from cluster centroids in normalized coordinates. So as we know that there are 35 observations and 6 clusters plus one more column that we are going to have, that is for the cluster ID. So we will like to have one column where we know which observation is assigned to which cluster. So that cluster is going to be represented by cluster ID. So and then there are going to be 6 centroids. So since this matrix is going to have the distances between all the observation and each of the cluster centroid. So let us initialize this 35 cross 7 matrix. Row names are going to be 1 to 35 for the observations, and then the column names, as you can see, first one is cluster ID, and then we have the distance from these clusters, which is actually distance from those cluster centroids. So let us change this. Then cluster assignment. So as part of the model that we have just built, in this particular attribute mod $3 cluster. So in the cluster assignments have been given. So let us have a look at this result. So you can see here in the output that the first column has been filled with data, and first observation has been assigned to cluster number 4, second observation has been assigned to cluster number 1, third observation has been assigned to cluster number 5, and fourth observation has been assigned to cluster number 5. So in this fashion we can see the assignment of these observation into different clusters we can see here. Now we are going to compute the distances between these observation and clusters, cluster centroids. So you can see here I am running a for loop where it is running from 1 to 35 for each of those 35 observations, and then the distance is being computed here between these observations and the cluster centroids. So we can see for each of these observations there are going to be 6 such distances, because there are 6 centroids. So let us compute this. Now we can see here in the output that all the matrix cells have been filled with the values. So the first column, as we discussed, the cluster assignment, and then distances of these observations from each of these clusters. So if we look at the first row, then we can see it has been assigned to cluster number 4, and its distance it's the distance from cluster 1 is given 2.38, its distance from cluster 2 1.73, its distance from cluster 3 is 5.17, its distance from cluster 4 1.51, and its distance from cluster 5 is 2.91. If you observe this first observation itself, you can see the distance of this observation from its own cluster is the smallest one, you can see 1.51. So that is why it has been assigned to this cluster. So so the distance of this observation from its own cluster centroid is the smallest one, and other centroids distance from other cluster centroid is slightly on the higher side. Similarly, we can analyze for other observations also. Now what we are going to do is we will order this particular output using cluster ID. So we will get all the observations which are part of the same clusters, and also their distances from the cluster centroids. So let us run this code, which will give us this output. So let us scroll up. So we can see here the first 4 observations which are part of cluster 1 are observation number 2, 7, 18 and 23. So these observations are part of cluster 1, and distances of these observations from 6 cluster centroids also can be seen here. Now we have, so from this we can see 4 observations are part of cluster 1, then followed by a number of observations which are part of cluster 2, then followed by 3 observations which are part of cluster 3, and then observation which are part of cluster 4, followed by, so in this fashion so on we can see the observations. We can identify these observations through the ID, and we can see so last one we can see that observation number 32, 33 and 34, they are part of cluster number 6. So we can identify which observation has been assigned to which cluster and their distances from these cluster centroids, and we can also see that these observations, they are closest to their assigned cluster centroid. So let us move ahead. Now if we are interested in looking at the coordinates of these cluster centroids. So till now what we have seen is that earlier that CC value, so this CC value, that this actually contains the coordinates for cluster centroids in normalized scales. So as you can see here, these are the 6 cluster centroid, and these coordinates, the different dimensions, price, energy, protein, carbohydrates and other variables, other dimensions. So these are these are coordinates in the normalized scales. If we want these coordinates in the original scales, we will have to use this piece of code, where you can see that the mean value for the average value for each of these dimensions is going to be computed, and then standard deviation value for each of these dimensions is going to be computed. Now these mean and standard deviation value are going to be used to convert the normalized scale value into original scale values. So, let us go through this code. First we compute the mean values, then standard deviation value, and then you can see here we are applying these values on CC, which is cluster centroid coordinates on normalized scales, and we will get the centroids on using original scales. Now, let us have a look at the output. So, as you can see now these centroids and their coordinates using the original scales. Now, you can see the price values, they are in their original scales. Centroid 1 is having the price value of 582.5, energy value of 360.15, and similarly other values. Similarly, we can look at the original values for other centroids. Now, all these computations that we have just done can be used for the next important next important computation that we wanted is the distance between cluster centroids. We are interested in analyzing the distance between cluster centroids because that can give us idea about how clusters are separated from each other, which is important because the objective of cluster analysis is to get the meaningful and insightful clusters, and looking at the distances between these cluster centroids will give us a sense about how separated these clusters are. So, let us compute this. So, coordinates in the normalized scales and in the original scales both we have. So, we can have a look at both of these outputs. So, so this particular piece of code is going to compute for us the distances between cluster centroids. So, let us run this. So, we can see here. So, here in this matrix we can see each of the 6 centroid and their distance with the remaining centroids. So, this is a symmetrical matrix, some of the values are going to be common. So, if we look at the centroid 1 here and its distance from other centroids 2, 3, 4, 5. So, we can see here. So, this centroid 1 seems to be closest to centroid 5. So, centroid 1 seems to be closest to centroid 5 and much far away from the centroid 6, that means cluster 6. So, centroid 1 and centroid 6 they are farthest, and centroid 1 and centroid 5 they are closest. So, this can also give us some idea about though we have these 6 clusters, which clusters can be joined and merged. So, this idea also we can get from here. So, let us move forward. So, original scale. So, we can also compute the original scales here. So, you can see the values in original scales, and also you will see the same thing. Centroid 1, if we look at the centroid 1, and we can see it is much far away from centroid 6 and much closer with centroid 5. So, similar kind of analysis we can do for other centroids also. Now, let us look at some other important piece of information. Now, what we are going to do is we are going to summarize these cluster distances. So, let us create this matrix where we have this is 7 by 2. So, let us initialize this matrix. Row names, you can see we have 6 clusters and then the overall results. So, that is why we needed 6, we needed 7 rows here. So, let us run this. 2 columns. So, one indicating the number of observation. So, we will get to know the number of observation in a summary format, which cluster is having what number of observation and the average distance that is there in cluster. So, that will also give us some idea about the dispersion within that particular cluster. So, let us run this. So, we will go through this part of code to find out this summary table. So, we can see here cluster 1 having 4 observations, cluster 2 having 6 observations, cluster 3 3, and then cluster 4 7. So, cluster 5 is the biggest cluster with having 12 observations. So, overall 35 as you can see. So, cluster 3 and cluster 6 are the smallest cluster having just 3 observations. Now, if we analyze the average distance in each of these clusters, we can find from here that The cluster 1 is having the smallest average distance among all the clusters, and it is much lower than the average. So, average is closer to 5, and the overall average is closer to 5, and the average in for this cluster 1 is closer to 3.5. So, there is a significant difference. So, cluster 1 seems to be having lower dispersion. So, it seems to be more homogeneous in that sense. If we look at the cluster 6, so average distance is much higher. It is almost double of the overall, and if we compare it with the cluster 1, it is much higher. So, cluster 6 seems to be having higher dispersion. So, less homogeneous cluster. Same kind of analysis we can also do using the original coordinates. So, let us go through this part of code which will give us that result. So, the similar kind of table, but now we will have the distances average distances in the original coordinates, that is all. So, this is the table as you can see here. First column is same, then we have the average distance in cluster that was using the normalized scale, and then the last column is having the original scale. So, we can see here that cluster 1 average distance is lowest, cluster it is. So, we can see here in terms of original scales results are more or less similar, but in terms of original scale the cluster 4 is seems to be having the lowest. Other results in comparable, if we compare these clusters, you can see cluster 6 is having highest dispersion, and cluster 1 and 4 and 2 are having the lowest dispersion. Now, let us analyze these results further. So, what we are going to do is we are going to create a parallel coordinates plot. This particular plot is going to help us in terms of characterizing these clusters. So, let us go through this part of the code. So, before we create the parallel coordinates plot, as we have discussed in our previous course when we were discussing the visualization techniques, we have to change the scales to 0, 1. So, let us do this. Once the data has been changed to this scale, we can use this particular library mass, and there we can call this function parcoord, which will give us the parallel coordinates plot. So, let us go through this part of the code. We can see here in the output. So, in this particular plot we can see 6 lines here, each representing centroids for their clusters. So, we can always analyze this particular plot in terms of characterizing these clusters. So, if we look at this particular cluster, this one, so this particular cluster is having the higher values for energy, protein, and many of the variables it is having the higher value, except the price is in the median range, and the last one rating is also in the median range. So, it is in terms of it is higher in terms of energy and everything else. So, it seems to be a more rich kind of cereal, that breakfast cereal that is there. So, in that sense we can characterize this. So, rich cereal could be one characterization for this particular this particular cluster. So, rich set of cereals can be one characterization. Similarly, if we look at this bold line, so this particular cluster and along with one more cluster, but this one more specifically is having values, lower values along all the dimensions. So, in that sense, if we look at this particular cluster, then it is having almost lower values along for all the variables. So, therefore, it can be it can be called low richness cereals, breakfast cereals, and we can see the price is in the lower side. However, rating is in the medium range. So therefore, this particular cluster can also be characterized as low low rich level. So in this fashion we can characterize different clusters depending on the kind of values that they are taking. So this is one way to understand the clusters and the characterize. Now what we are going to do is next we are going to create a plot. So for this we are going to use this particular library cluster, and this plot is going to be 2D representation of clusters. So even though there are many dimensions because of the presence of many variables, but those variables are going to be brought down to 2D labels. So 2D representation of clusters is something that we are going to create. So this is the function clus plot that is going to be used. So in this we will get this output. So first we are passing on the data, then we are passing on the cluster assignments, how these different clusters the different observation have been assigned to different clusters, and this information is going to be used to create a 2D representation. So let us run this. Before we run this, let us clear the previous plot so that we get a more clear picture here. So this is the plot we can see here. So in this 2D representation, this is 2-dimensional component 1 and component 2. However, this is good enough 2D representation because we can see that these two components explain 70.83% of the point variability. This is much similar to what we did. This is like multi-dimensional scaling, what we did in PCA. So this analysis is quite similar to that, but what we are seeing right now is the graphical representation of that analysis. So we can see here the cluster number 6 and the points that are observation which are part of this cluster 6, which are clearly visible in this plot. And we can also see that these points or these observation, these serials are also average distance is high, right. If we look at the other clusters, so they are more a bit of overlapping clusters. However, let me remind you that this is a 2D representation of the whole clustering process. So you can see cluster number 2, the observation which are part of it, cluster number 1, cluster number 4 and observation which are part of it, cluster number 5 which is very closely going along with the cluster number 1, and then the cluster number 3 is here having just 3 observations. The cluster number 3 and 6 having just 3 observations, and we can see other clusters having few more observations here. So in this fashion also we can understand the clusters, and the characterization process that we did can also be completed. So with this we would like to go back to our discussion. So let us go back. So few more points about specifically about the k-means clustering. So how do we evaluate usefulness of these clustering results? So one metric that could be used is the distances between final clusters that can actually be used to compute this ratio, the sum of square distances for a given k to the sum of square distances to the mean of all records. So this particular ratio value will give us about the idea about whether the clustering results are useful or not. So this is more about understanding whether the clusters are separated or not. So if the clusters are separated, then probably the clustering results are good. So this particular ratio will give us that indication. So the value of this ratio comes out to be closer to 1, then probably clustering has not been effective and there are too many overlaps, significant overlaps. If the value of this particular ratio is small, then probably we have well separated clusters. So if we have well separated cluster, then it is more likely that the clustering results are going to be useful, and as we have seen in the R studio in the R exercise, that we can always characterize them, analyze them and generate meaningful insights from them. So that is the end of cluster analysis. So we will stop here. Thank you.